Hi guys, welcome to Learning Electronics Repair, and today we're going to talk about PFC. Yeah, this is all you need to know about PFC to fix stuff. So what is PFC? Well, in the term of electronics, it is power factor correction. And you will find plenty of websites and some videos explaining to you what power factor correction is, using some nasty mathematics and talking about things being 90 degrees out of phase and blah, 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 blah. So I'm going to do it without any of that, yeah. But I'm hopefully going to do this in a way that you can understand it. So, power factor correction. This is basically to do with the efficiency of a circuit, how efficiently it uses the energy provided to it. If we talk about a circuit which is purely resistive, yeah, it's a resistive load, and we feed an AC signal in, let's say mains, live, neutral, okay, what you're doing is you're applying a sine wave. This is your AC mains, 50, 60 hertz, depending on where you live. So this squiggly line represents the change in voltage over time, okay? Let's make it a bit bigger. This is positive, this is negative voltage, and over a period of time, the voltage goes up to the maximum, back down to the minimum, back up to the maximum, and so on, okay? And the frequency of this is known in hertz, and this is 50 hertz, means 50 times a second, or 60 times a second in the USA, because you're a little bit faster than the rest of us, okay? So there we have a change in voltage. With a load which is completely resistive, what's the current that's flowing? Well, the current depends on the voltage, and the higher the voltage, the higher the current. So at the same time the voltage is doing this, the current is doing the same thing. As the voltage goes up and down, the current it draws goes up and down. Yeah? And this is known as the power factor. So here the power factor is 1. All the energy going in is being used in current, and watts, which is power, equals voltage times current. Okay? So for a resistive load, the power factor is 1. All the energy is being used. Now what happens with an inductor? Or for that matter, a capacitive load. But we find inductive loads much more commonly, okay? There's an acronym for this. This one is CIVIL. And it stands for capacitors. I'll put caps because it's shorter, yeah. I, current. V, volts. Look, I don't have the space. I, in this case, current, again, and L is an inductor, okay? And what this means is that for capacitors, current leads voltage. This makes sense. When we charge a capacitor, before we can get any voltage across the capacitor, we have to put current into it, yeah, because it charges, okay? The other half of this, VIL, voltage leads current in inductors. This is not quite so intuitive, but basically with an inductor, it has inertia, like a water wheel. So before the water wheel will spin, we have to put some water pressure on it. Voltage is the pressure. Current is what's flowing through the water wheel, but it needs to spin up. So we have to apply pressure before we get any current going through it. Yeah, so voltage leads current in inductors. I hope that was also a bit intuitive. We all love water wheels, yeah? So with an inductive load, we have the same thing. AC, plus volts, minus volts. Same waveform, same frequency. Okay. What's happening with the current? Well, the current, which is the orange line, yeah, orange current, how about that? Yeah. So the current doesn't start flowing until some voltage has been applied. And if we were going to do any maths, which we're not going to do, you will find, or just remember, that the current is 90 degrees out of phase. So this is 0 degrees, this is 180 degrees when it's upside down, back to 0, and in between is 90 and 270. So the current starts to flow here. Okay. This is so difficult to draw and keep it looking like it should do. Okay, there you go. So you'll see that the current is out of phase with the voltage. This means that the maximum current is not flowing at the same time we have the maximum voltage. Yeah, can you see that? So at the point when we have the maximum voltage, we don't have the maximum current. At the point when we have the maximum current, we don't have the maximum voltage. That means that effectively the power factor is less than 1. The device is not using all the power we're putting into it. Okay. The power we're putting in is still watts equals voltage times current, and voltage and current are continually changing in relation to each other. Okay. And the power the device is consuming, we measure as VA, which is volt amps. It's kind of like watts, but it takes into account this lack of efficiency due to the power factor. Energy companies, being what energy companies are, they charge you for that. Yeah, they charge you the money for that, even though what you're actually using is that which is less. Okay. How about that? So this is one reason why we need PFC, power factor correction, and the other one is it's just better for the environment. Yeah, if we use energy more efficiently, that's good for everybody, apart from the power companies who now make less money. So what power factor correction does, it brings this current more into phase with the voltage, ideally totally in phase. But in actual fact, nothing is ideal in this world. Have you noticed that? Yeah, nothing's ideal in this world. But we can get to about 0.5% convergence between the two waveforms, current and voltage. Okay, so that's what PFC does. Now we know what PFC actually does. Let's have a look at how it does it. So there are two main types of PFC. There are passive and active. Passive PFC is generally used on low powered power supplies and also on some older power supplies, because the active PFC came a little bit later and originally was more expensive to implement. To be quite honest, now with the cost of components, it's probably cheaper for the manufacturers to implement. So these days you either see no PFC at all. If it's a very low power supply like your little wall warts and such like, because it draws so little power anyway, it isn't really worth the cost of implementing the PFC. This is the sort of thing you will find in particular on ATX power supplies, computer power supplies, TV power supplies, your LED TV, those sort of power supplies will have PFC, again because it draws quite a bit of power and the device is operating for long hours. Yeah, so this is where we find PFC used. So passive PFC is something that's kind of like a bit out these days, but if you are working on more vintage equipment you may see it. So let me just show you how it works. We have the same thing, live neutral. This is your mains coming in. And we have an inductor coil before the bridge rectifier. So this is your bridge rectifier. AC, AC, plus, minus. This is your neutral. Obviously you'll have a fuse. Well, hopefully you'll have a fuse, a switch, okay, maybe a NTC thermistor to stop the inrush of current when the capacitor's charged, but none of that matters for this. Okay, we then have a capacitor here and we have across the coil capacitor, resistor connecting like so. These are called the PFC capacitors. won't quite fit in there, but PFC capacitors. This is your PFC inductor, okay? The point of this circuit, and I'll just draw the output, so we have the bridge rectifier. This is your DC, around about 320 volts, okay? And this goes to your load, whatever you're supplying power to. In this case, the load will be the switch mode power supply itself, which drops that voltage from 320 down to 5, 12, whatever you need, okay? The point of this circuit effectively is to try to get the current and the voltage back into phase, because your inductive load is shifting it by 90 degrees. That's also shifting it by a certain amount as well, and the combination of the two is intended to bring the phase between the current and the voltage back together again, okay? The circuit is not 100% efficient or even 95% efficient. Because we have fixed value components, it will vary in performance at different frequencies. This is not really generally a problem because our mains is either 50 Hz or 60 Hz. The other problem is that this inductor will be quite large, physically large, which means that in modern terms quite expensive to manufacture. So I will show you physically what this looks like in a moment, but let me just draw the active PFC and then we can look at some actual examples, okay? So active PFC. This is different. In this case you have your bridge rectifier again, AC, AC, plus minus, and on the output then we have a circuit, the PFC circuit. So again, this uses an inductor, but this is a small inductor compared to that one, and I'll tell you why in a moment. We have diode, and then this is your large smoothing capacitor, and again this goes to the load, which in our case again is the switch mode power supply itself, okay? We have a resistor here, and then we have a controller. So the controller, which goes across this resistor, this is your pulse width modulator. We have a MOSFET here, okay? That's driven again by the controller. The controller will take power from here, a startup power, okay? This is your ground lead. This one is your current sensor. This is a current sense resistor. And this chip measures the voltage across this resistor. By doing that, it knows how much current the load is drawing, okay? Voltage equals current times resistance, and if you know the voltage, you know the resistance, you can work out the current. So that's what that's doing. And this will also have another connection which is monitoring the voltage here as well, okay? So it's monitoring the output voltage from the PFC. It's driving this MOSFET, and what it's doing is it's switching this on and off at very high frequency. What that does is when the MOSFET is switched on, it connects this end of the coil to 0 volts, or hot ground we'll call it. This is effectively ground, but it's also connected to the mains, yeah. It's not isolated. When the PWM switches the MOSFET on, current will flow through here. Again, we'll get this 90-degree shift, okay? And before this coil can fully magnetize, it magnetizes with the current. This is switching back off again. The coil now demagnetizes, and the voltage at this end of the coil increases, and that goes through the diode and charges the capacitor. So what we have with this circuit is a very high frequency switch and an inductor. What it's actually doing is two things. First of all, instead of having the situation where we have the current lagging the voltage by 90 degrees, okay, what we have now is this MOSFET switching on and off hundreds of thousands of times within that waveform. So it's switching on and off all the time. Yeah? On, off, on, off, on, off. And each time it switches on, it draws current. So it's switching on and off so rapidly that although we still technically have this 90-degree shift, within the time this is on and off, when we're near the peak of the waveform, we still approximately have the same voltage and the same current at the same time. Okay, you see that? So effectively your output is like, it's going to be very hard to draw this. Voltage, and the current is, I can't use thick pen, I have to use something else, guys. The current is like rapidly changing like this. Okay, can you see that? You imagine like it's doing that hundreds of thousands of times a second. Okay, so the current is doing that, and what we basically get is an extremely close approximation between the voltage and the current waveform, and the efficiency, as I said, is about 0.96% maximum. Okay, so that's what the active PFC is actually doing. One of the things. The other thing it's doing, I mentioned, when this inductor switches off, the magnetic field here collapses and creates more voltage at this end than there was originally. Okay, so the voltage here, if it was smooth, which it could do with a capacitor, would be about 320 volts. The voltage here is higher, and the diode only conducts one way, that way. Okay, conventional current, positive to negative. So this boosted voltage goes through to the capacitor, but it can't come back. So the voltage on this capacitor will go to around 380 volts, up to about 400 volts, something like that. Okay, often 380. So as well as getting this current and voltage waveform almost in phase, even when it's not in phase, if you see what I mean, lots of little 90-degree shifts like that, yeah. As well as doing that, it also boosts the voltage, so it's a booster. And the DC voltage then going into your switch mode power supply is boosted, it's higher. This active PFC, because this is switching on and off very rapidly, hundreds of thousands of times a second, that causes high frequency switching noise to come back. Okay, so with active PFC you will also find that we have inductors here, or we should have if the power supply is being designed properly. Okay, we'll have a capacitor here, usually, quite probably another inductor as well. Quite probably this pen's run out. Okay. These are double inductors, so they're like one in the live, one in the neutral. Okay. Another capacitor here. And then this is your live and the neutral through a fuse and an NTC normally. NTC to stop the current rushing in to charge this capacitor. Because even if this PFC isn't working, look, positive and negative, as far as DC is concerned, that is just a short circuit. So even before this is running, or even if this is not running, we'll still get the 320 volts coming in and charging this capacitor. Okay, that's why we need a pen that works. NTC resistor here. And we also will need a fuse. Yeah. In there, live and neutral. So you will also find this type of filtering at the front end of a power supply using PFC. Now let's have a look to see what this looks like in reality. This is an old ATX power supply, probably best part of 20 years old. This is from an era where we had mainly passive PFC or none at all. Okay, and this metal bracket here, if I can just remove it, this has the inductor, this big coil here. This is not a transformer, look, there's just one winding. So this is the PFC inductor, passive. This is the PFC capacitor that we talked about. This actually is another filter, basically the same as this sort of arrangement. And then the fuse, that's probably the NTC in there. This is where the mains comes in, okay? So we can see it here. These little blue things will be MOVs, metal oxide varistors. These are basically there to get rid of any voltage spikes and surges on the mains, okay? So that is what a passive PFC looks like, and you see all this is before the bridge rectifier, which is how I drew it here. Here is a power supply with active PFC. This is faulty, it has some components removed already. So what we have here is the mains comes in here, onto here. Okay, this is your fuse. Again, the input filter, that's this stuff. The NTC thermistor, which is there. Again, these are the filter capacitors, these are these ones, and the bridge rectifier, okay? And then there's wires which go from here to the PFC, and this is your PFC board. So what we have is we have the inductor, that one, that's here, okay, this is an inductor. We have the diode, which is actually that device down there. If you look, I'll just show you. This is a diode. May look like a transistor, but it is a diode. Can you see the symbol on it there? See the diode symbol? Okay, so that's the diode. These, in this case, two of them, are the switching MOSFETs. That's this MOSFET. Ours just has two in parallel to handle more power. And this chip here, L6562, this is the pulse width modulator and control chip, the PFC controller. This B plus, this is your supply coming in, okay, and then out there, that goes back to the big smoothing capacitors, which we can see here, okay. The only other connection to this board from the main board is the hot ground, the ground connection. So that's what a PFC circuit actually looks like. On this power supply, it's a separate PCB. On many power supplies, it's integrated onto the main board itself. You can usually tell with an ATX, at least, if it has PFC, active PFC, if there are three of these large heat sinks. They are usually all on the one PCB. This one is the PFC. This one is the switch mode power supply, the primary side, the switching transistors. And this one is the rectifiers on the output side. These are all your connections, 3.3, 512 volts. Okay, so that's what PFC circuit actually looks like. Now, what can go wrong with these things? Generally speaking, passive PFC, this type, doesn't really go wrong. If this coil went open circuit due to excess current, that would cause the circuit to fail and you would get no output. If this capacitor was short, that would blow the fuse and you would get no output. But generally speaking, this doesn't happen. If this was open circuit or this resistor, it just wouldn't do anything, but the thing would still work. You just lose the efficiency. You would still have power getting through into the power supply and the load. Yeah, so it doesn't go wrong, really. And if it did go wrong, in most cases, you probably wouldn't notice, okay? This type is very much like a switch mode power supply. It has a switching MOSFET and a pulse width modulator controller. The most common failure is the MOSFET goes short. This diode could go short, it could go open. In honesty, that's something I haven't particularly seen. I think I have seen them short, but it's not common, so bear in mind we need, in this case, to test the diode, we need to test the MOSFET. So that's the initial checks with this. If you have one not working, these components, this low value resistor could go open circuit. Again, it's not a particularly common thing, and the chip itself could fail. But generally speaking, unless there's some problem elsewhere in the power supply causing it to draw too much current, this probably in itself won't fail. There is another failure I have seen sometimes. This chip is drawing power from here, okay? And it's not just connected like that. Normally there's a high value resistor or several of them in series here. And they go open circuit or high end value. So this never gets enough power to start. If it doesn't get any power to start, it won't run. Will the power supply still work? Probably yes. Because if this isn't working and there isn't a short here to stop the current flowing through here, through the diode in that direction and charging this capacitor, unless you have, as I say, some sort of short here, you will still get 320 volts in the capacitor here. And your switch mode power supply will happily run from 320 in almost all cases. So you can often find a PFC that isn't working, but the power supply will work. Again, you probably won't notice the difference. It's not running as efficiently. It could cause problems with whatever the power supply is driving or the power supply itself, but technically speaking, it will probably run. Okay. That means that if you have a PFC problem and you have, for example, often in the TV, one circuit board which has both the PFC and the power supply and probably the circuit that generates the constant current for the LED backlighting as well, all in one, and you want to know, have I got a problem somewhere else as well as in the PFC? If you take this MOSFET or MOSFETs, pair of them, out, and this diode is okay, or you even bridge the diode, you short it, when you plug in, the PFC will not run, but the power supply probably will run. So that's where you can diagnose those sort of issues when you have one large PCB containing a lot of different parts of the device and you're not sure exactly where the problem is. So you can disable PFC often, and that's quite a good repair technique, okay? You also find in some power supplies, if we just complete this diagram, you'll basically see what I mean. So this is going into your, I'll draw it like this, it doesn't really matter, this is not most power supplies, but this is going into your switching circuit like this, okay? MOSFET or transistor, this is your primary, these are your secondaries, and this is controlled by the switch mode power supply pulse width modulator. So this again is switching very rapidly. This is your switch mode power supply, okay? You will sometimes find that that chip and this chip are both the same chip. It's combined pulse width modulator and PFC controller all in one. In this instance, a fault in this part of the circuit can damage or destroy the chip. So this also doesn't work. So that's another issue you need to consider when you're working on power supplies that are faulty. They have PWM and switch mode power supply. Easiest way to figure this around, to be quite honest, is to find the controller for either, look up the data sheet, and you'll know straight away if this is a combined controller like this, or we have separate pulse width modulator for the PFC and pulse width modulator for the power supply. So that's another thing you should just keep in mind. One other thing I'll mention, and this is because this can be quite dangerous, okay? Normally, with a power supply, if the load, the switch mode, isn't running when you plug in, assuming there's no shorts here, what will happen is that the large capacitor will charge up 320 volts and it will stay charged. It may discharge after a while, leave it a while, or you can discharge it using a resistor yourself if you want to make it safe to work on. But inherently, the power supply is in a dangerous condition. You've plugged the mains in, it doesn't come on, nothing appears to happen. You disconnect the mains, you've got a nasty 320 volts in those 1 or 2 large capacitors waiting quite happily for your finger to come along, and then you'll find out, So a lot of us know this. If you didn't, you know this now. What do? We come to repair the device, we plug it in, nothing happens, okay? We unplug it and we think straight away, have I got a high voltage in this capacitor or capacitors? So you need to get your voltmeter and measure to have a look. Where do you measure? Well, when you're looking at a circuit board like this one, the capacitors are here, and until you get the circuit board out of the power supply, you can't get under there to measure to see if there's any voltage. But you can be quite smart, because what you have here is the bridge rectifier, and we can see the legs of that one. So we can measure across here and here with our multimeter and see whether or not there's any charge in this capacitor before we start to dismantle the thing. And if you don't touch it with your fingers, touch it with the metal chassis, and that'll make a big flash and a bang, and you might not be electrocuted, but you probably need a new pair of trousers, okay? So that's what we would do. We would check across the bridge rectifier, because in many cases we can get to it. What happens in this circuit? Well, again, if the PFC isn't running and the power supply isn't running, when we plug in, AC comes in, rectified to DC, straight through this piece of wire, effectively at mains frequency, straight through the diode, and the capacitor charges up to 320 volts, just the same. We've got 320 volts in the capacitor with no load on it. We unplug the power, there's nowhere for the 320 volts to go, so it sits there waiting for you. I'm waiting for you, okay? Same situation. So, clever, I'll test across the bridge rectifier, because I can't get to that. I measure across here. I will always read 0 volts. Why? Because this diode, this one, is preventing you from reading the voltage across the capacitor by reading across the bridge. That little beggar is just waiting for you, because you weren't prepared. It still has lots of voltage to give you a good zap. So with PFC, remember, you cannot check if it's a dangerous voltage here by measuring there. That's important, guys, okay? So that's probably all you need to know, really, about PFC. It's not a difficult thing. It's not a difficult circuit. Usually if it goes wrong, it always goes wrong in the same way, or same ways pretty much. One thing I didn't mention, I'll just point this out now, you kind of knew this, but you didn't know this. Because the PFC is a booster, and it will boost the voltage up to this, and it's using pulse width modulation. If the voltage coming in is lower, then this will increase the on time of this MOSFET to draw more current into the inductor to increase the output and try to get the output up to that. And this circuit can work in a very wide range of voltages, and that's why you find all these devices these days, let's say 80 volt to 40 volt or something like that, They'll work in that range because the PFC, by changing the duty cycle, can counteract between these voltages and work, okay? So, bonus. That's why we see that on modern switch mode power supplies. Okay, hope you enjoyed that, guys. You know where the comments are, down there. Let me know anything I didn't cover. Tell us about it. Anything you think I could have explained better. My explanation of the PFC and those graphs, I use no maths. If you say it wasn't correct, let me know, but find a better way to explain it using no maths, okay? So there's a challenge if you need one. Otherwise, tell me, that was pretty good. Okay, look forward to seeing you all soon on Learning Electronics Repair. Ciao for now, guys.